We have something brand new this year, and we're very excited to continue our collaboration with the Carlson Milley program and the entrepreneurship program at the business school across the river. On the wrong page. So we try to do new things every year. This year, by the way, across from the registration desk, please walk into one room is Hands on Hearts lab, and the other is a visualization lab, including some 3D representations in virtual reality and airway projects. We were on TV this morning. Rob Sweet, MD, is Rob here? He was on TV, and then at 10 o'clock on Channel 5 we'll be on again. But the exciting thing is that we have now a medical technology innovation program. Again, I'm on the wrong page, sorry. Emerging Medical Innovation Evaluation Competition Awards. And Steve Parenti, head of Milley, approached us about adding this to this conference. And this is the 3 and 5 this morning you might have been at, very exciting technology, and this is business evaluation. And so we're privileged to have Randy Nelson to come up, who's part of that program, and describe it for us. Randy?
Good afternoon. We started this program this year as an offshoot of what we do, three semesters every year, fall, spring, and summer, in helping companies and individuals evaluate their technology to see if it has any practical application. As you've probably seen in the past, there's a lot of really good technology that never makes it to market, and it's generally not for a technical reason. It has to do with business practices, maybe IP, marketing, different hurdles that get in the way, and that's what we try to help entrepreneurs, whether they're at the university or outside, understand. So that's the Medical Industry Evaluation Laboratory as part of the Milley program. So we started this in 2008 by listening to people and seeing what needs to be done to help entrepreneurs understand earlier whether they should continue what they're doing and whether they have a good chance of raising funds, or whether they should go get grants, or what would be the option would be. So we looked at it two ways, both for the benefit of the university, the student population, but also for the benefit of the entrepreneurial community. And it's really broadened out from the Twin Cities. We've done projects from different parts of the United States, so people have come to us from all over. So what it is a graduate level class. It meets once a week, and we go through different projects. This spring we'll have gone through, by the end of the spring we'll have gone through 16 different projects. So it's a pretty rapid fire process and a lot of learning on the way. Give you an idea of who takes the class. It's very, very unusual, not only for the university here, but for universities in general. Steve Parenti was able to get a letter of understanding from 8 different schools within the university to work together to be able to have graduate students take this class. So the whole idea was to have people from different disciplines just evaluate a technology just like a major corporation would. They wouldn't just get their business people together. They'd get somebody from a patent office, from marketing, from engineering, all these different areas to look and see whether something was worth investing in. So that's what we do. And we, most of them are working students, some of them are full-time students, and but it gives us a good broad range in being able to look at a very wide range of medical technology, whether it's devices, pharma, software, anything that falls within the genre of medical technology. So what's listed here is a full-time laboratory managing director, Steve Parente. Faculty co-directors, there's myself and Mike Finch that act as the faculty for teaching the class. And then at the beginning of every semester, we bring in for a full Saturday experts in the area. So we have somebody talk about intellectual property, somebody about marketing, on clinical, on regulatory reimbursement, an investor looking at it from a small company perspective, and somebody from the strategics looking at how the strategics look at early stage companies. So it's a very full day, but it gives the students, some of which have no experience in medical technology, a really good head start, and then they're usually available during the semester. 2 goals. So one is for the students. Of course, it's a teaching opportunity for students, not only to understand and evaluating medical technology, but how to think really fast and make decisions. They've got 5 weeks to figure out some rather complex problems. So they spend a lot of time as a group understanding all these different dynamics, and many of which don't exist in the rest of the world. Regulatory reimbursement, for example, clinical studies, for example, to be able to give the entrepreneur a good idea of where success may be, or whether they should just go do something else. And it can be all over the map. So, and they always look at it, as in this last bullet, as though they're looking at it for 2 audiences. One is they're acting as the investor. Would I invest in this? And then for the inventor, they're letting the inventor know where would there be obstacles, whether it's the market's too small, there's too much intellectual property, you'll never get it out, or there's a better market opportunity. So there's all kinds of different options here that the inventors, who typically are more technically oriented than business oriented, give them a good head start as they are approaching funding. And then for the entrepreneurs, it's giving them that insight on how to approach investors, what to talk about, whether they should be approaching it in a different way, and it gives the inventors essentially a first look at how their presentation, how their idea is going to come across. Sometimes it doesn't come across well, not because that it's not a good idea, they just don't know how to talk about it. And if they were to go to an investment community, they'll get written off right away. They won't get a second chance. So here we give them an opportunity to get that right. And then, is it a good idea? As in the real world, most ideas have a lot of struggles and a lot of challenges. Every so often we'll hit some home runs and we'll say go as fast as you can. But most of the time it's pay attention to this, find a new market, here's your intellectual property obstacles, you got to work around that, and help them out so that they can decide whether they're going to move forward or not. So that's kind of an oversight of the lab. It's been really good experience for the students, some of whom have gone into some of the strategics, some of whom have stayed outside of medical technology, but they've learned how to think a lot better than they had before. So over the start, we've evaluated 172 different technologies, and this isn't very easy to read. The biggest one up there is, as you can imagine in this community, it's cardiac. And the rest of them are software, different types of devices. It's all over the place. So a team never knows what they're going to be evaluating next. So we started the first annual competition, to bring in companies and individuals that have ideas that they want to see what can be done. So there were 15 different individuals that submitted ideas from different parts of the country, and from that we brought it down to 5 different presentations that were made yesterday at 4 o'clock. And of these, there were, that's where we came down to the 3 that we'll present today. The tough part is all these are good ideas. And so we actually spent quite a bit of time after the presentations going through these to see which had different merits, and it's not that I discourage anybody, but they all have challenges. At emerging companies, everybody has a challenge one way or the other. So we came down to 3 different technologies that we thought were worthy of the awards this year, and we'll go through those right now. So if the inventor can come up after I put this up, then we'll give you your award. So, well, let me talk about it in a minute first. So here's the judging criteria, and this is the same thing we do in the Millie Lab. So in the end, is it something that's feasible? And how much challenges there are going to be to get from point A to point Z eventually. So the first one, reduction of medical implant infections. Dr. Wistenberg? So as you can see, this is an antimicrobial. It's an area that's become very popular, and they have an idea that may have some real benefit, and it's an early stage company, so it's got a lot of trials to go through as well. The second one is a NOTES, which is natural orifice procedures, closure of esophageal punctures and fistulas. Robert? See here? There he is. So the first one was a Minnesota-based company. This is Toronto.
It's now an international competition.
Yes. Okay, and then the first one, the smart micro instruments for advanced interluminal interventions from Joshua Gafford out at Harvard. So as part of this, they'll all be able to take advantage if they're interested in going through the Millie Lab and get a good solid business analysis. This has been a good opportunity. Hopefully that we can add some value from a non-technology point for them and help give some guidance. And this is a competition that we're planning on doing every year. So it's been interesting. The first year it's taken more of a national, or it's the international with Toronto being in there, to give entrepreneurs a good idea of how to pursue and how to progress in the future. So, thank you.
Thanks, Randy, and the Millie program for doing this. I think this is a great addition to the program here. So we'll plan on continuing it. Well, it's my pleasure to introduce our keynote today, and the tradition now, actually 9 years, we've been giving this award out, the Medical Devices Center Award, and we will have then the recipient give a presentation, and I think you're going to really enjoy this. The past winners I'll just mention, Peter Gove, who was at St. Jude at that time, Dale Wallstrom, who was here this morning, he was at BioBusiness Alliance, Fred Cohen, Boston Scientific, Rebecca Bergman at Medtronic, but if you haven't heard, she is the incoming president of Gustavus Adolphus College, and what a great opportunity for a PhD biomedical engineer with lots of experience at Medtronic to go into a very famous college in central Minnesota. So that's exciting. So if you got this award, who knows what's going to happen? I'm sure it was the first page on her resume. Then we had Rich Nazarian from Minitronics, Tim Lasky, who I think is here from Medtronic, and Randy Schistel, I know, is here. This year, we are just pleased to recognize the contribution of Just Herder. He had volunteered a couple years ago to run a first ever Design Medical Devices Conference Europe. And I think you got about 250 people there last October, and this was a new venture for both of us. Before that, he was working on the paper competitions. I first met Just through the American Society of Mechanical Engineers, and every time he gave a paper, I was sitting there thinking, doggone it, why didn't I think of that? What you'll find, I think it'll come out in this presentation, is he's the kind of guy that sees the simplicity in what doesn't look simple to everybody else, and that's both in the invention side. So I think he's a right brain, left brain guy with lots of gifts, but also in the equations, and both he and I have our roots in kinematics, mechanisms, and robotics and dynamics, and that keeps on happening. Every time I hear one of his students make a presentation, boy, is that a nice, simple solution to a difficult problem. So we are just pleased to have you come up, and thanks for accepting this award.
Thank you very much, Art. Finally, you can have your own lunch. Let me see. All right. Thank you very much for your kind introduction. It has been really a pleasure being involved in this conference and earlier on in ASME. And it's a great pleasure to show some of the work that Art referred to, as well as some latest unfinished ideas that we're working on. So I work 4 days per week at Delft, and every Tuesday I go all across the country to Twente University, which is a 2-hour train ride, so it's not so bad. And so I'm actually appointed at 2 universities, and I'm trying to use the energy of both of the groups to synergize the efforts of the groups into joint efforts, which is very nice for the students who get to see at least 2 environments. And what we do is all mechanisms related, as Art pointed out. So you can see some robotics, some grasping, some mechanisms, and I will show a couple of them in the course of this presentation. What is also very nice is that some of the students take their inventions and build a startup company around it. And here is a couple. On the right, there are some medical related companies, and there are some others as well. And collaborating with those startup companies is very nice. There is this simplistic model of valorization where people think, well, the knowledge is on the shelves of the university, and if you just shoot it to industry, then money will flow back. Well, it turns out it doesn't work that way. One of the reasons probably, if I get money, I spend it on my latest ideas, which is not necessarily the startup company. So what we try to do is to stay in close contact with those startup companies. And what happens usually is that they take their proof of concept and want to turn it into a product. And they ran into all kinds of problems. And it's not just a matter of tweaking. No, it has to be 10 times smaller, 10 times cheaper. So lots of fundamental questions are raised, which flow back to the university. And that is very nice, because that gets us to work on relevant problems, which are very challenging, and thereby we can set up joint projects together with the startup companies, and that generates this cycle based on information or knowledge flow rather than money. And that's very interesting, and generates a lot of additional activity. All right, what's this about? Well, any motorcycles among you? Motorists, motorcycle riders? Yeah, there's a few. Well, this is a motor skills training course on a circuit. And my wife and I have only one motorcycle, so I'm just sitting here and taking pictures of my wife. That's actually not why I'm showing it. I want to point out something about the motorcycle. You may recognize it's a Ducati, very famous international brand, very successful in racing. And this is the engine. And particular about the engine, it's a 2-cylinder in a 90-degree setup, right? You can see 2 cylinders, one pointing forward and the other one pointing up. And this concept was conceived by Fabio Taglioni, also known as Dr. T. And he had a very strong motivation in creating fast motorcycles. And he came up with this motto which worked for him. And what worked for him is striving for simplicity. And not just simplicity, pushed to the farthest extremes. That was his motto, and it worked for him. And he put together this motorcycle. The engine is very narrow, which is great for aerodynamics, but also for cornering. And with his team, he managed to put the Ducati brand as a #1 race team. Why am I showing this? Well, it is important to develop this design philosophy, if you will. If we look at design, then typically we have lots of parts, like motors, bearings, and we put them together into what we call a concept. And the concept has some behavior, and we can measure that, and then we have the performance. This may be power output or mechanical efficiency. And if we're not happy, then we iterate, so we run through this cycle again. So we pick other parts or different parts, put it together maybe in a different way, and run this cycle again. Now there's a couple of observations that you can make. One is due to the law of diminishing returns. It's also present in engineering sometimes. Because what happens typically is that we focus on the performance. So if we're not happy, we're going to improve the performance. And typically we manage, all right? So we modify our concept and it does perform better. But at the same time, there's also a cost involved, right? The concept may become a little bit more heavy, takes more energy, that kind of thing. And if we're not careful enough, then we are caught in this trap. Another thing is that we really cannot blame the parts. The parts are fantastic. Ball bearings are a minor miracle. If you look at it from a kinematics perspective, it doesn't work, but still, it works actually very fine. And the motors are very well designed, high efficiency, etc. So it's really on us, the way we put things together, if we're not happy. And a third observation is that generally we are very good at determining the behavior from a given concept, right? If we have this concept, we can determine or predict, if you will, the behavior very well. We have very sophisticated computer models and software that help us. But what we really want is to define a certain behavior and then find a concept that does just that. And that is difficult. Now, how do we get around this? And think back about Dr. T. What we are trying to do is find the essence of the desired behavior. And once we know that, then we can try to generate a minimal embodiment to realize this behavior. And it sometimes helps to define the behavior in somewhat optimistic or even impossible terms. For instance, I mentioned energy efficiency. Yes, it will be great if we can reduce the energy consumption. But what if we take it one step further? What would that be? Maybe we can find a system that doesn't use energy at all. Oh, that's even better. And what if we take it even another step further? What do we get then? What if we design something that actually generates energy? And once we are able to pose that question, then typically we find a solution. So very often, posing the question is more difficult than finding the solution. So try to think about impossible terms. For instance, sit to stand. Very common problem, very hard to solve. What would be the essence of this problem? Well, first of all, I don't know either, because it's not labeled there, right? That's the problem. So maybe it is insufficient strength in the muscles, or maybe the person needs some guidance. Maybe it's a matter of physical condition, or some support is needed, or whatever. And then it's our job to convert that into technical specifications, like maybe we need a force device. We may need to design a force generator, so we express it in newtons. Or maybe we need some motion guidance, and then we can define a path function. Or maybe it's a matter of stability, because what we observe is that people are able to get up right to the moment where they have to let go of their armrests. So they actually can get up, but it gets stuck somewhere. So hypothesizing about what is really the matter is the first essential step in innovative design. And if you can make a difference here, then you're likely to get a real new invention. All right, now my table of contents, finally. This is actually an interactive list, so I can click any of these topics. And I made a pre-selection. So let's go ahead for now and select the first one. It's about a design of a prosthetic hand. So imagine that you are supposed to design an artificial hand. Then, what do we get? And this is actually one of my favorite diagrams. It's unpublished yet, so you actually get to see something new here. And what are the benefits of the hand prosthesis? Well, hopefully every now and then it helps you. For instance, in dressing, it's very hard to get your zipper closed with one hand, so if you have another one, then that helps a lot. And in eating, brushing your teeth, and getting dressed and all that. So every now and then you have this benefit, and that's really great. That's important. However, at the same time, there is also the burden of wearing. It's heavy, it's a little bit sweaty, and the thing is, if you integrate this over time, then the red area is likely to be larger than the green area. So that's why many of the hand prosthesis devices end up being unused. So what do? Well, of course, we're going to improve the design. Okay? So if we do that, what do we get? Oh, higher spikes, maybe a few more spikes. That's great. But beware, at the same time, we may also increase the mass or the energy consumption. And the question is this design any better or not? So it's again the diminishing returns. And in English, you guys can phrase it very nicely. There is a great risk of doing the wrong thing better and better, right? So again, how to escape this? Well, let's try and think about the essence of grasping. So what we're really trying to do here is push the red area back. And then it is getting in better proportion. So what is the essence of grasping? Again, nobody knows. So we can hypothesize of what is really the essence. So we can do in a little experiment. You can try and grasp your glass of water. So go ahead and grasp your glass of water. And who of you can tell me exactly what you did? What did you do? Did you move your hands and fingers across a pre-programmed path? I'm not sure. And about the results, do we care much about where the fingers end up or how they got there? I'm not sure. Yet motion is the first thing that we think of if we think of grasping, right? But is it really the essence? That is the question. So maybe it's something else. And at some point we hypothesized maybe it's the distribution of forces that matters, not so much the motion. actually, if you think about it, you get a conflict if you want to control the motion, because the object is already there and it has a shape. So it doesn't really make much sense to control the motion. So that's why we thought, well, what if we can create a device that generates forces irrespective of the motion? Well, at that point, we had no clue on how to do that. So there was something like this impossible behavior. But after a while and a lot of waste paper, we came to the following idea. So instead of mimicking some natural motion, which may look nice, but may not guarantee a stable grasp, instead of that, we are going to design something that distributes forces rather than anything else. In the end, of course, it's the same mechanics, but from a design perspective, it's a major difference. So this is what we ended up with at first. Here you can see a finger, which is composed of two phalanges, a proximal one and a distal one. And there is one cable which is driving the system. And the cable branches out here. One branch goes to the first and another branch goes to the second phalanx. So from a robotics perspective, this is a very odd system because you cannot control it. There's 2 degrees of freedom, 2 joints, and only one actuator. So there's no way to control the motion of this finger. But what we can do is we can optimize the geometry of this part here so that we can optimize the way this force is distributed over those 2 phalanges. And we can optimize that for a range of motion. And then we know whatever motion happens, the forces will be distributed the way we designed it in. And that's what you can see here in the video. So it's a little bit hard to see, but the tendon is going up and it's driven by a constant force, no control whatsoever. And you can see here that it tends to make contact with the object, which is the hand of the student in this case, through a wide range of motion. And only at the extremes it loses contact here. So there's no sensor, no control whatsoever, it's just a pull. And the rest goes automatically. And here's another version. It's linkage based. Here you can see another finger. It's composed of in fact it's a 5-bar linkage, but let's consider the point where it touches an object. Then the driving torque here stalls, and let's consider this one as the base for a moment. And then we identify a 4-bar linkage here. And this little link here is the coupler link. And from kinematics we know that it tends to rotate about this point, which is called the instantaneous center. So it's like as if the distal phalanx is pinned down here at this point. So imagine the contact force. If it passes distally of that rotation point, then of course the phalanx tends to rotate clockwise, right? But it will be blocked here by a mechanical stop. So the finger is stretched. However, if the force applies at the other side of the pin, of the joint basically, then the distal phalanx tends to rotate counterclockwise. And that is not stopped by this mechanical stop. So then the finger will actually flex. And this is what you see here. This is the grasper, which grasps the object between the tips. So the force is distally of the instantaneous center, and the fingers are rigid, right? So we have a pinch grasp, precision grasp. Now below you can see the very same gripper, the very same object, but the object is elevated a little bit. So the forces apply at a different location, in this case proximally of the instantaneous center, and you will see a totally different behavior. Oh, how about this? Yeah. So the fingers envelope around the object. And again, there's no sensor, no control. It's just an on-off control. You switch on the motor and this happens automatically. So we call that self-decisive. I'm not sure if that is English. Okay, let's go back to our table of contents. This is a topic about a surgical tool. And we were confronted by surgeons who said, well, you know, we have no feel of what we're doing in laparoscopic surgery. And actually, it made sense to them because, you know, the instruments are steel, and steel is you know, not very friendly material, if you will. So intuitively, it made sense that you wouldn't feel anything about the tissue. However, it turns out that the instruments that are used are in fact linkages with pin joints, and there's a lot of friction. And that's perhaps remarkable because we have a lot of sliding journal bearings in many devices that work very well. In your car, for instance, the crankshaft has this kind of bearing and it works perfectly fine. The difference is, of course, that we cannot lubricate it here because they are sterilized and then they're clean, and we basically have dry contact between stainless steel and stainless steel, and that's pretty much the worst combination that you can have. So it's understandable that there's no feel in those instruments. So what can we do? Well, we can pick different bearings that may solve the issue, but you know, these ball bearings tend to be quite large and need to be duplicated as well. And we can also connect sensors in the jaws. So we measure the force and we feed it back to the surgeon. That's perhaps a circumventing strategy. But we were not quite happy because these would be quite complicated systems. We thought of perhaps something more simple. And rolling is actually a nice idea. If you finished your glass of water, you might do another experiment. If you would lay it flat and roll it, you will find it rolls very efficiently with very little friction. And that is actually the idea that got us to work. The only thing is that it's quite slippery. If you would just roll it like this, it may slip away very easily. So what we did in addition is connect a flexible band. So you might use your napkin if you're in for an experiment and wrap it around like this, and you will feel it will not be able to slip to the left anymore. Okay? And you could still roll it very nicely like this. Okay? So we like that, and turns out there is actually a concept called rollamide that does this in a very elegant way. So what if we connect a couple of jaws to this? Then, since the rollers roll in opposite sense, we automatically get a gripper. Very nice. The only challenge here is to how to drive it. So we thought of an additional band, flexible band, and if you pull it, it will close. Here is our first prototype. It looks a little bit rusty, and I actually intentionally let it rust to show that even with inferior materials, you can get a very nice high efficiency as long as you are rolling. Unfortunately, miniaturizing this didn't work because the band was not strong enough, so we did another design iteration where we changed the direction of the surface such that the main forces would be taken by this surface. And we also wrapped the napkin a little bit more sophisticated in both directions, so it wouldn't be able to escape both ways. And we ended up with this concept. Here you can see the roller again. So this is your glass of water. And at the other end of the instrument, there's another one. And they are connected by these rods here. And they are also in rolling contact with these little pins. And this is how it moves. If I remove the auxiliary lines here. Essentially, it is a parallelogram, but a very strange one, because it has only rolling contacts and no sliding contacts anymore. And because it is a parallelogram, it also has a very nice one-on-one moment transfer function. That is also something that the current instruments do not have. So you can predict very well what your action does with the tissue. And here you can see our prototype. And if you look carefully, you can recognize the cylinder here, the green one. Here, it comes out every now and then, is the connection rod, the red one. And these glossy little parts here are the flexible bands. They're 30 micron thick, and they went through hundreds of students' hands, and they're still alive. So it's amazing. And also in some experiments that we did, we found that the perception is very, very nice. Okay. Now, there's one issue still with those rolling contact joints. Assembly is a little bit challenging, and perhaps also cleaning, because of those flexible bands that wrap tightly around the cylinders. So we went to yet another strategy, which is called compliant mechanisms, which are mechanisms that move due to deformation. So there are no sliding parts. In fact, there's only one part, and it moves due to deformation, which is great. There's no friction. It's very easy to clean. There's only one fundamental problem. Because there is deformation, you need some energy to deform it. And that is usually considered as, necessary evil. It's it's a feature of the concept itself. So the output energy is always less than the input energy, and therefore sensation is also challenged. However, the energy here is not lost, it's not dissipated, it's just stored. So what if we recycle it? Then we get this very strange scheme with recycling of energy, which theoretically appears to work, but the question is how to implement that in a device. And it turns out to be possible. So again, if you pose the right question, then the solution is nearby. And here you can see our very first crude prototype with a gripper, which is a compliant gripper. It has a positive stiffness, which means that I have to put in energy in order to deform it. But here, on the other hand, there is a preloaded spring mechanism, which has energy on board already, and it moves along with the gripper, and as it moves, it gives some energy to the system. So in total, the energy is constant, and it seems as if there is no stiffness at all. And we did the same experiment, and indeed we were able to feel the pulse in an artificial artery. The next step, of course, is to turn this beast into something more elegant. And here you can see an artist impression of what we are aiming for. Again, the compliant gripper, but now the balancer, as we call it, is also fully compliant. So we end up here with a single piece surgical tool, which has no friction and has no stiffness in the motion direction, so you don't feel it and you don't feel anything. So this has become our ideal device. And here on the right, you can see one of the first prototypes that we made. In this figure here, you can see how it works a little bit. Here's a gripper, and here is another version of such a compliant compensator. And you can see, if I run it again, that it has multiple equilibrium positions. You can put it anywhere. So it seems that there is no stiffness, but in fact, it is all internally balanced, and everything you feel in the hand grip is actually related to the tissue force. And we were able to get smaller devices and smaller devices. This is this one is etched based on lithography techniques, and that is very relevant because currently chips just calculate and they already run hot and they get all kinds of issues related to heat generation. And imagine the next generation integrated circuits, they will also have actuators on board, and then of course energy consumption will be even higher. And we have to be very careful in creating energy efficient micromechanisms already now, even if the applications are still years ahead of us. So that's something that we're working on right now. And here you can see a few examples of those devices. You can also see that the force is not yet entirely zero, so there's still some work to be done. But in any case, this is one of the things that we are working on. This is one of the better ones that we have produced so far. It's a 5 millimeter by 1.5 millimeter mechanism, and it produces a very near constant force. over its range of motion. It is actually built out of carbon nanotubes. Hopefully you are able to see the individual tubes here. This is one of the junctions somewhere around here. And the mechanical properties are fantastic. It's amazing. There's hardly any hysteresis, so this is a very promising way. And it can also be made sterile and everything, biocompatible. In the interest of time, I will go a little bit faster. And the idea is that basically, if you do a force analysis, then it turns out that if you support your arm somewhere here, you can try it, or you can even try it with your neighbor. And probably you do it every week in the bar, where you put down your arm like this, and even after a few beers you will still be able to maintain equilibrium with very little effort. And that means that instead of creating a complex system, I need to support only this point of my arm, right? And we do know devices that do this, like an ordinary desk lamp. It carries the mass of the shade through space. So basically what we did is we created a desk lamp for these patients. And you recognize the structure here. Yeah? It looks like a desk lamp. The only thing is it carries 4.5 kilograms. And here you can see the difference between one arm on Earth and one arm in outer space. This is Eelke. He cannot use his arm very much just because of gravity. He has some hand function. But if we remove gravity by this force generator, constant force generator, the desk light, then you can see what he can do even the first time he is trying this device. Okay. And what we're recently doing now is converting all this functionality that I was showing into less parts. We call it compliant robotics or shell mechanisms, all kinds of fancy words. But basically what we want to do is integrate many functions into few parts. You may remember this finger with all the functionality, the automatic grasping. We're now turning it into a single compliant part. So here you can see is another finger. And it has more or less the same behavior. It adapts to the environment. It behaves differently if there is an object in the way. But it is only one part. And also for the body support systems, instead of the exoskeletons, which are fantastic devices, but they are less suitable for nurses, for instance, who are treating patients. And in our country, 80% of the nurses get lower back pain sooner or later. So we want to supply them with a support structure, which is essentially one part, a compliant part, which moves along with their body, but as it moves, it generates some support force against gravity. So that's actually something that we see a lot, devices for healthcare workers, because we have to be very careful about them. Not only nurses, also surgeons. Here you can see it actually works. This is one of our subjects who is willing to try it out. This is a very first crude device, but even in this one you can see the EMG from the situation without the device reduced as compared to with the device. Okay. I would say it's time to stop. But not before I'm going to encourage you to, when you get back to work, to think about whether you're doing the right thing instead of the wrong thing better and better. Thank you very much.
Well, I think we have some time for questions. Yes. Can we, right back there.
Mies van der Rohe from Bauhaus, less is more is the German expression for what you do. I was sitting here thinking with your anti-gravity, my father-in-law just had a stroke, that this would be marvelous for rehabilitation, and there's another component to it because your brain has to reconnect as well. So there's another dimension to this.
That's absolutely right. Thank you very much for your remark. This one was initially intended for as an assistive device for people with a stable condition, but also for one thing we found is that apart from providing some functionality, it also provides physical therapy, because people are able to move and therefore they will move, and that is very beneficial for their whole condition. We haven't tried out rehabilitation cases so far, but there is interest. What we probably need to do is add some control and actuation, because typically if people are still progressing, you want to be able to tune the level of support that you supply. Yeah. Thank you so much.
Yeah, thank you, Jess, for a very provocative talk about design and design process. As you think about creating these designs, for example, the complex mechanisms in terms of getting there, do you recommend starting with something that, say, has pin joints and might be a little bit easier to understand the behavior, and then moving towards the in one case it's a simpler design, but in the hands more complex, or just plunging right in from the beginning? So what's kind of the fastest way to get to the end point as you're thinking about prototyping and thinking through designs?
Well, thank you, Will. A friend of mine says, my favorite CAD is cardboard-aided design, and I tend to agree wholeheartedly. As I pointed out early on, typically we don't really know what we need to design. We have to figure out what is the essence of the device we're trying to develop. And certainly in that phase, it makes a lot of sense to do some quick and dirty design with regular available materials, and get some feedback as soon as possible. Typically, if I have a project, I try to build in as many prototype steps as possible. So I'm not sure if that answers your question, but yes, it's a great danger for all of us, including myself, that we want to present the ultimate design at the end of the project term. But it's better to have some failing versions in intermediate steps. Yes. So yeah, you may have noticed that I presented this idea of trying to find the essence, and of course we fail. We fail every day. We just hope that we're failing at a slightly higher level every day. And that is actually where design and research sort of blend together. We are hypothesizing about design philosophy, and then we're trying it out. So our design is essentially a test setup.
I was handed the microphone, so I guess I have the next question. You posed the question, what is the essence of the sit-to-stand problem? Can you give us some more thoughts about that?
Yeah. Again, I don't know, but I have the feeling that people can do a lot more than they think or than they dare. And currently I have the idea it's more like a stability problem than anything else. Because one thing we tried is to apply rubber bands to a person's trunk. So the rubber bands were preloaded a little bit, and the forces were all in a horizontal plane. So by providing that compliant network, we did not apply any vertical forces. And the person was able to move up, and because we provided some stability in the horizontal direction, at least this person felt a lot more confident and was able to get up from the chair. Without any power that we put in, it's just some stability. So from that quick experiment, we concluded that maybe it's not necessary to develop a force generator. Maybe it's not necessary to provide a motion generator that would help the person choose the right path. But maybe it's enough to provide some stability. And, that will result in a totally different design than if our mindset was to design a force generator. I hope that answers your question. So the short answer is I don't know, but...
So I'd like to give just a token of our appreciation. We have this tradition of doing a globe for the winner of the Medical Devices Conference award. And the award is really given out. He did a wonderful technical presentation, and it's simple elegance. And I invite you to Google his work. You'll see lots of spring balance mechanisms that are so simple and elegant. The award, however, is being given out for, as we do every year, for someone that's really contributed to the community in the medical device space. And I forgot to mention that he was also associate editor of our ASME journal, and he's also has brought Europe to Minnesota in many ways and runs his own conferences in addition to the contributions that I mentioned. So he's really a well-deserved winner of this year's competition. So thank you, Just. So now it's back to work. Please enjoy the sessions this afternoon, and don't forget that we have the poster show over at the stadium starting at 5:30.